Hey everyone, I'm Ty Smith. I'm the Android platform tech lead at Uber. I'm here to talk a bit today about how we make developers more productive that are doing mobile development. So real quick, this agenda is going to be, we'll go over a little bit about kind of the scale that we're operating at. Then we'll look into the organization, kind of how we think about that. Give me a second to make my speaker notes a little bit bigger. There we go. Then we'll talk about how we do measurement, so like what DevX looks like when you're measuring that. We'll talk about making your builds faster, move into some of our IDE work, and then if we have time, I expect this might go long, so we'll have a reliability section that I may end up cutting. So a little bit to talk about our scale. We started as a small startup in 2008 and went through a bunch of hypergrowth and very quickly became one of the largest apps in the world. We evolved our architecture along the way, and now we have mobile apps that are well over 10 million lines of code. Very large. In general, we have thousands of microservices, hundreds of thousands of deploys per month, over 10 public mobile apps, 7 programming languages, 5 big platform monorepos, hundreds of millions of lines of code. And if we dive into mobile specifically, we have a bunch of mobile apps now, many business lines. They're all using a converged architecture called RIBs that we've talked about in some previous talks. That's a Viper-like architecture. So our mobile apps are over 10 million lines of code, tens of thousands of build modules. We have over 600 mobile engineers. So we're going to talk a bit today about how we help those folks be productive and have a good developer experience. So to go a bit over the workflow that folks have at Uber. We have 5 platform monorepos, so we have 2 backend, Go and Java. They both use Bazel, and then we have an Android repo, an iOS repo, and a web repo. For iOS, that's also on Bazel as well as web. For our Java and our Android repo, we currently use Buck as the build system and are migrating to Bazel, which we're going to talk a little bit about. For the mobile engineers, we have a number of apps that sit on top of a converged tech stack. So that's standard library, standard architecture, build tools, a shared observability pipeline, shared networking stack. And this allows developers to keep consistency when they're building that many apps, that many modules, and can keep context as they move between different parts of the repo. Real quick, just to kind of give an idea of like the amount of scope we're talking about, we have our own custom architecture, which is open source, called RIBs. It's Viper-like. We make very heavy use of modern Kotlin with Compose for our data flow, coroutines for our data flow, and Compose for our modern views. We have our own DI that's open source called Motif, which fits really nicely with our RIBs architecture. We have our own storage library that's open sourced called Simple Store. We are doing a lot of like custom UI work. We have a standard design language called Base. We've open sourced Base Web, not yet for the mobile, but we will be doing that soon. It's based on Compose. We're building our own SDUI pipe on this. We have our own standard kind of data and observability stack where we have custom crash reporting, custom analytics. That's all in-house. And then on the build side, I mentioned we have Buck and Bazel. We also have our custom annotation processing that we're using for the faster builds, which we're going to talk a bit about. We use BuildKite for sharded CI that's containerized. We do a lot of custom IDE and developer tools work. So we have a lot of IDE plugins that we build in-house, Flipper plugins. We have our own UI hot loading tool called Quick UI. Our own analytics stack for developers called LDA. We make heavy use of a lot of reliability linters like detect, KT format. So in general, we're not going to go over all of these today, but I kind of want to point out, like, if you're a developer at Uber, you have a large stack of things. It's the standard way of doing development. So we want to talk a little bit about the organization, like how the people work in this big org. So typically you have 3 different kinds of teams. You have teams that are building features. They're building the end apps, the Rider app, the Eats app, et cetera. Those are the feature engineers. You have infrastructure teams. That's like my team that's doing all the platform work, libraries, build tooling. And then you have some hybrid teams that may have some product customer they're serving, but they're also serving a reusable library. Payments might be a good example where there's an entire payments platform, but they have an end customer. So if we take a simplified look at just the mobile teams, we have 4,000 engineers, so there's going to be hundreds, maybe thousands of teams at Uber. But specifically for some of the mobile teams that y'all will find interesting, and we'll give you the context, we typically have the mobile platform, which is my group, and we serve developers and build all of the standard architecture and everything else. And then we partner with the platform team in the writer org, and the driver org, and the eats org, and a handful of other teams throughout. And then we're serving all of those feature teams that I talked about. And then we have a cross-cutting guild for mobile across the entire company called ARC. And then we kind of do that similar model for the other domains that we serve as well, where we have guilds of the very senior staff, principal engineers that kind of sit in that. If we zoom into the mobile platform group, that's not one team, that's many teams. We have an Android developer experience team, a foundations team, which is building frameworks. On iOS, we have counterparts of both of those, a mobile networking team, a mobile data team that's focused on observability and analytics, a dev tools team, a custom bug reporting, mobile UI. We have a bunch of different teams that are kind of serving all of the 600 mobile engineers that we have. So my org's vision is to be the industry leader on how developers build, deploy, and manage high-quality software productively and at scale. And the strategy that we follow to kind of, for our vision, for planning, we need a balance having fast libraries, powerful libraries, and fast tools. So the developers get both kind of the architecture side and the build tools side. And without a heavy set of safety nets, then we would lose focus on reliability and quality, and then obviously the developer experience would suffer later on. And then we can only do this properly by standardizing across the board. So we have nearly 30% of the 4,000 engineers are polyglots, and they work across mobile, backend, web, data. And so if you have that many folks moving around and you have a large set of custom infrastructure, custom tools, there needs to be a lot of standards so that folks can do that effectively and not have a huge amount of onboarding time as they move between different parts of the stack. So all of that context kind of gets us into how we start to think about what developer productivity actually is, which is, I think, why you're all here. So let's start with how we measure that, right? Like, what is DevX, developer experience? How do we have metrics around that? How do we think about prioritizing that? How does a company say, hey, this is valuable for us to invest in? So this is the way that we view mobile code development. We have, the software engineers, their inner loop, which is very quick. It's, run, edit, build, and they're doing this as they're producing code. Then they, put that up, they run local tests, they put that up to CI, it goes for code review, that goes to our submit queue, which is a merge queue that funnels everything in before it lands on main. It goes to a CD pipeline where it's pro-guarded and redexed. Then, there's a build cut that happens every Monday, and it starts an intensive QA process with automated and manual. And then we start a very slow rollout to customers. Beta release first, followed by incremental rollout in production. So as this is happening, as issues are discovered later and later in the pipeline, they're more expensive, right? This is a cost to the organization, and it's a cost to the engineer. So optimizing in that front, shifting the error states left to the developer is going to be a drastic improvement. So how do we measure that? How do we think about that? Well, there's a number of different things that we measure. Probably the biggest one is developer satisfaction, or NPS. If you're not familiar with NPS, or Net Promoter Score, this is a metric that's publicly used often to figure out how folks would recommend a specific product or service. It asks on a scale of 1 to 10, would you recommend this to someone else? And it counts 1 through 5 as detractors, people who are negative against your product, 6 through 8, I believe, as neutral. They don't count towards your score at all. And only 9 and 10 are considered promoters. So the idea is it's counting detractors versus promoters to figure out how that looks. And then we track a lot of hard metrics, developer throughput. So that's everything from amount of PRs they're putting out to how long reviews are taking to how much focus time they have on average per team. And then we track a lot of granular metrics, local build time, the failure rate, like when exit codes are thrown because a test failed or a compilation failed, how long Git's taking, how the IDE is performing, all of CI/CD, its time, its uptime, and then app performance and reliability as well. And there's lots of other things, but this is kind of the high level of how we think about tracking some of these. So let's dive into NPS just a little bit. Here is NPS over time for all of Uber engineering. As you can see, it started out very negative, but in the world of NPS, getting above 0 is a pretty strong accomplishment. Most NPS at 0 most people consider this neutral. So this is kind of demonstrating the growth of that as we've been doing these cycles in developer feedback. Our last one probably had about 2,000 respondents, so that's kind of the sample size that we're talking about when people discuss this. And in addition to the NPS score itself, they're also giving us lots of feedback on what parts of the stack are hard, what's easy to use, where they feel productive, where they feel bottlenecked, what kind of freeform feedback they have. And then our org, which is focused on developers, and many other orgs take that feedback in, and they're able to make positive changes or roadmap adjustments based on developer input. And then we get into some of the more interesting technical side of this, which is how we think about measuring the local development experience. So we have a pipeline and set of tools called LDA, Local Developer Analytics. And so this runs a daemon on the local developer's machine. And we have a number of data collectors. So a data collector would be things that are integrated with the tools that folks are using. It could be build, it could be get time, et cetera. And those are emitting events that are pooled and then sent up to a log collector service, which throws those up to Kafka for storage. And then we have a ton of backend tooling that allows folks to query this, set up monitoring, set up dashboards. And then we can use that organizationally to figure out how we're prioritizing or responding to certain events and debugging problems when they occur, which is really interesting. We'll see like a spike in build times, and we'll correlate that to something that landed in our diff pipeline, and we can see that we had a regression on a certain set of developers' machines from a change that went in, which becomes a really powerful debugging tool. So to dive in a little bit more, locally, we have integrations with Git, Arcanist, which is what we use for code review right now, Buck, Bazel, Gradle. We have a custom set of IDE plugins that emit to the analytics pipeline. And then all of our custom CLIs and tools have a standard API that they emit to this as well. So we'll get into a few more of those custom CLIs a little bit later, and keep in mind those have this integration as well. And then what does that give us? So it allows us to do really interesting dashboards like this. This is our IDE dashboard. We have similar ones for build, for Git, for all of the other tools that we're doing. And we're able to get really granular metrics from our developer community on indexing time, code analysis, UI freezes, memory usage, crashes, all kinds of stuff that we have instant access to, and helps us develop, debug and prioritize work, as well as understand the impact of the changes that we make. And then thinking forward a little bit more, those very granular metrics are great, but it's hard to have an org that says we're going to move these 7 granular metrics up, right? You want to have aggregate metrics that you can think about and you can communicate to leaders or to stakeholder teams that are like, hey, we're moving the performance you care about, and that's how we're investing. And so there is a standard measurement protocol called AppDex, which is developed by an alliance of different companies. Now, this is also how JetBrains themselves are thinking about measuring in their enterprise tooling moving forward, although it's pretty immature from their stance so far. And what this does is it allows you to set thresholds where you have tolerating, satisfied, and frustrating experiences for the developer. So whatever the tool would be, you could say it's the IDE, or you could say it's build times or some random latency on a service. You would set these thresholds, and then you can have one or more metrics that are in aggregate communicated to that, and then you can track how your work is affecting that up or down. And then this is something that we're investing in now that we don't have a lot of built out yet, but we'll be using this going forward for most of our tooling and how we communicate that. So moving on from the measurement side just a little bit, we're going to move into builds. Now, a little history of our build systems at Uber. This isn't going to be a talk necessarily on like why you should use Bazel or Buck versus Gradle and what those differences are, but I'll give like a really quick overview of what that looked like for us. Back in 2016, we moved off of Gradle to Buck because of performance problems. Once we had in the many hundreds or thousands of modules, we were using Gradle with a plugin that we wrote called OKBuck to generate the build files, and developers continued to use that for dependency management. Then in 2019, we continued to hit scaling challenges with the even little bits of Gradle that we had left that was using for dependency management, but it needed the entire configuration cache. This was before configuration caching and the other stuff that Gradle does these days. So we moved entirely to checking in our build files and being pure on Buck and kind of moving most parts of Gradle out of the stack. In 2021, we started evaluating seriously moving from Buck to Bazel to align with the rest of the industry, where we've seen many of our other big peers move to Bazel, and we've seen maintenance problems with Buck from Facebook and low adoption there as well. So we wanted to consider being on something that had a community investment, that we could align with other partners, and that had forward-looking techniques that we wanted to take advantage of. So we started that migration en masse this year. That's been ongoing. We expect that to take until mid next year when we can fully deprecate all of Buck. At this point, it's mostly running in a shadow mode. We are working seriously on a lot of the performance problems that we've kind of identified, and we're closely collaborating with the community. So we're working with Snap and Spotify and Lyft and Airbnb and some other folks that are either in the middle of a migration or seriously considering a migration or planning it. And we're maintaining the Kotlin rules and working with Google, working with JetBrains on the IntelliJ plugin. So it's a lot of community engagement this year while we kind of finalize what's needed to do the full migration. And then next year, we'll be deprecating Buck once we have the performance problems out of the way. We'll talk about those performance issues here in a minute. And then we can look into some forward-looking advancements like remote build execution, where you can shard out your builds to a number of machines in the cloud. Why would you want to consider Bazel or Buck any hermetic build system, really, compared to Gradle? Well, you probably wouldn't unless you're getting into larger size applications. There's some downsides we'll talk about, but on the positives, it's a hermetic build system and it guarantees reproducible builds. It's highly parallelizable. It's really aligned with the industry, not just Android, but all big monorepos. Most big companies are kind of moving in this direction. So there's a lot of investment. There's a lot of commercial partners that are starting to develop third-party products for it. It has a dedicated build language called Starlark, which is a really lightweight version of Python. Now, while Kotlin script or Groovy are really powerful languages, it makes it really easy to have side effects in your build system where you break the cacheability in Gradle, and this really kind of bulletproofs a lot of that. So you have more guaranteed caching, and for developers, it's typically a better experience once you have an infra team that's supporting that. There's also forward-looking advancements. I mentioned remote build execution. And then as an infra team, we are converged with the other teams at Uber who have already migrated, so we're able to share large amounts of resources. Any investment in one, because it's polyglot, is kind of an investment in all of the stack. And it's very easily extensible. What are the downsides? Why wouldn't you? Well, it's really lacking an out-of-the-box experience. It's not for the small app, the indie app, the small company. Typically, it does require dedicated engineers, or at least it does right now. Maybe will come a point when it's mature enough that it really doesn't. And then it's also slower for new Android features. There's a lot of things we build ourselves with Buck or Bazel. When KSP came out, there's a Gradle plugin for it. We wrote the integration for Buck, and then we worked with the community to get the integration for Bazel. And so it's slower for things like that. So let's give a little bit of context to why building at the scale we're talking about is really challenging. So here's a graph that we use LDA to populate, which shows the number of locally built targets for a developer that's working. So if you're in the Rider app or Eats app or our Driver app, this is the number of targets that the 75th percentile of folk are, which we use to measure local builds that aren't clean builds. So this is the number of builds that are not coming from, or number of targets not coming from a cache. So we'll see, for the Rider app, for every iteration, they're building up to 200 modules. And they're caching thousands of others and using those and linking those, but 200 modules. Comparing this to one of our backend monorepos, which follows a much more traditional microservice model where it's very, very flat in the build graph, it's 2. So build times for backend engineers is very, very quick because they're building 2 modules at a time, while every time you want to build and test the Rider app or the Driver app, you're building 75, 100, 150, depending on the size of it. This is a visualization that I had a lot of trouble getting out of GraphViz because of the number of modules. But this is the writer dependency graph. It looks like a big blob at this level. Maybe if we zoom in a little bit, it's a little more comprehensible. Not quite. Okay, that's starting to get there. So this is over 12,000 targets, and they're very intertangled, as you can see, which means often a change in one of these has a large set of side effects and requires building a lot of other modules. So you could start to see why incremental changes would require 200 other targets to be rebuilt. So if you're not super familiar with how build target invalidation works and like how dependencies work in build systems, I'll give you kind of a quick overview on that so we can talk about some of the optimizations. So if we have 4 nested modules, foo module depends on bar module, depends on foo bar module, depends on baz module, and I make a change when I build foo module, I have to build the lowest one first. And so baz module's built, that's returned to foo bar module, then it's built, then it's returned to bar module, and then that's built and returned to foo module. So if I make a change in baz module and I build foo module, I'm gonna have to build everything up the stack. To make that a little more challenging for us, we did a study back in 2018 or 2019 that was on our Eng blog to measure Kotlin performance in large-scale repos. So we used a ton of generated code, and we were able to measure a lot of different scenarios. The fastest on the right, you'll see JavaC without any compiler plugins, but we make very heavy use of error-prone, which is a static analysis tool built into the compiler. So at that point, JavaC and Kotlin, JavaC with our full stack, with error-prone, with annotation processing, with everything else, is about at parity to vanilla Kotlin. But as soon as you start to add in annotation processing, mixed Java and Kotlin sources, different rounds in the compiler, those sorts of things, you'd very quickly get to Kotlin builds taking twice as long as Java builds. So when we're talking about 12,000 modules needing to be built and 200 targets and our developers suffering times, at the time that were, maybe 100 seconds, if not more, for every change, that's a lot. And so we had a lot of investment that we needed to do into the build system and into the compiler before we pushed really hard on Kotlin adoption. So I'll talk a little bit about some of those and how we got to where we are today, where we have a pretty large set of Kotlin migrations happening. So for thinking about faster compilation in the compiler, I need to give a little bit of context into some core concepts. Inputs and outputs for a build module, cache keys, and then ABI jars. So we'll talk about these in order. So if you have a build module, it takes a set of dependencies. It also takes configuration, toolchain information, all of those sorts of things. And that's called an in, or an input for the build target. Now, all of those together, along with all of its dependencies ins, are calculated to produce a cache key. And that cache key is just a hash that's used by the build system to understand, hey, can I pull this thing from cache, or do I need to rebuild it? And then it outputs, a jar or an AAR, or if it's a non-JVM target, maybe it's SO files or whatever that looks like, and that's the output of your build target. And so a build target typically has one output. Now, the other concept I mentioned we need to understand is ABI jars. So if I have foo module and I have bar module, and foo depends on bar, and I make a change in bar, do I need to rebuild foo? Well, the answer is it depends, right? If you're an ABI jar, actually let's take a step back for a minute. We'll explain what we're doing here and then how ABI jars help with this. So let's say we have a module that has one source file in it that has a method called bar, and it's producing a string called foo. Now, I compile that, and I get a class file that looks similar to the right, where I have my Kotlin method has become the full jar that has a static final string method bar, and then its implementation is return foo. So if I make a change where now instead of returning foo, I'm returning foo bar, the method didn't change, but the implementation did, the output, the class file changed, right? And so because we're hashing that entire thing to produce the cache key, the hash is now different. So our cache key changed, and the build system needs to recompile what's upstream from the module. Now, ABI jars are interesting because it solves this problem to a degree. If I have the same method that has the body foo, and I produce the jar from that, if it's an ABI jar, I have stripped the internal implementation. It's just the method signatures. So at this point, I take a cache key of this, and it's just a jar of all the method signatures. So if I change the internal implementation, because the body is stripped, it hasn't changed. The cache key is the same. So in this case, if I've made a change in bar module and I compile, I only need to rebuild bar module. I don't need to rebuild foo module. So we talked a bit about kind of the three top concepts. Now I want to dive in a bit into the different types of ABI jar modes. So first is how a build system produces a class ABI jar. Now, what this is you have the module, it runs through Java or Kotlin C, and you have your full compilation that comes out of that. You have a class file, you have your cache key, it has the full implementation. But then the build system hands this to another tool that uses ASM to strip out the implementation and produces a second artifact, which is your ABI jar. So you've had the entire cost of the build for that single module, and then you have a second artifact, which is the ABI jar. Now, this is great. Like, it gives you both of the things that you want. And that previous example where we didn't need to rebuild the top module is true, but I did all of the work that was required on both. So that's where source ABI jars become a little more interesting. A source ABI jar is similar, except it uses a compiler plugin that's built into Java or Kotlin C. So you have your module, it goes into Java C, and then it outputs both the ABI jar and the bar and the regular jar at the same time. So this doesn't require that second step where we hand it over to like an ASM stripper. Now in Java, this is more interesting because we can do further optimizations. In Java, the compiler is typically running in 4 stages: parse, enter, analyze, and generate. Now, we have all the information we need for the ABI jar by the time the enter stage is done. And so some build systems will allow you to emit the ABI jar early, and that will then, and then it will continue on with the rest of the compilation. And so you have them at 2 different times. So this unlocks a really cool thing called rule pipelining, where you can have 2 modules that depend on each other. You start to build one, it emits the ABI jar, and then continues on. When it emits that ABI jar, it unlocks the parent to start building right away. And so they can start building in parallel, even though there was a dependency of one on the other. But when we get into Kotlin, the story is not so clean. We have a Kotlin compiler plugin produced by JetBrains called the JVM ABI Gen plugin. When you do that, it still produces the ABI jar and the regular jar at the same time. By the time you have produced enough information in Kotlin C today, without the K2 compiler, to produce an ABI jar, it's within a % or 2 of being able to emit the final jar. And so that overhead isn't worth it right now. So we need another concept before we can kind of put some of this together, which is, we talked about how mixed Kotlin and Java sources were slow in that analysis that we did. So let's walk through an example of how that works. You have one module that has a foo.kt file and a bar Java file. Now, we hand that to a compiler factory, and it runs Kotlin C first. It runs foo.kt, it takes that as an input, and it takes bar.java only for analysis. It's not going to output anything from that. So out of the Kotlin step comes the Kotlin's class file, foo.kt, and foo.class. And then we take the Java source and the Kotlin output, and we hand that to Java C as the next stage. Now, Java C can then compile the Java sources, and then we hand that to a third step, which is a compression step. So we take the foo class file, the bar class file, outputs from both compilers, and we jar that up into a single jar. So now we have a module that was mixed sources, and we have one output from the build system that is a jar that contains both of them. So what is challenging about that, and actually let me go back to kind of explain this. This is challenging because you have this one output, right? And so with Java, we're able to unlock downstream dependencies to start building early. But if we're doing mixed sources, we're unable to because it requires everything to be jarred together until the very end, and we have the single output. And so what we would see is if we had a pure Java module, depending on another pure Java module, it was faster than a mixed source set module plus another Kotlin module. So pure Java plus Kotlin was faster than a mixed source set with the same amount of Java and Kotlin because there was advantages in the Java compiler that we could not take advantage of here. So I'll talk a little bit about how we resolved that to some degree. We had the rule pipelining from Java. We wanted to build a hybrid mode for mixed sources. We know that we can't output early from the Kotlin compiler, but we can from the Java compiler. So what we did is we built this hybrid mode where we give everything to Kotlin C, and it outputs the foo class and the ABI class at the same time. And we hand both of those, or we hand the ABI class and the foo class to Java C. And after its parse and enter stage is done, we can emit early from Java C. And Java C is going to continue. So now we have a full Kotlin class file and an ABI Java C file. And we can compress two of those together in one step as a ABI jar. And then we can let it compile and finish and emit the full jar. And so what this does is this gives us parity, right? Kotlin C is still slow. It's slower than Java. We recognize that. But if you have one mixed source set module with 2 Kotlin files and 10 Java files, that has performance parity with 2 modules, where one module is pure Kotlin with 2 and the other is pure Java with 10, whereas before it did not. So what does this look like in practice? Here's a trace graph to kind of demonstrate what that looks like. By the time we are getting into the analyze and generate step, as soon as we have the ABI jar, before that finishes, we're able to move on to foo module. So even with both of these being mixed sources, we're able to emit early and save some bottlenecks in our build process because these are more parallelized. So we talked about ABI jars and pipelining and how that can make faster builds. Let's talk a bit about per-class compiler avoidance, which is taking this one step further. If we have an example here where foo module has 2 dependencies, but it only uses 1, why do I need to build both of them? Well, because we're using ABI jars, it doesn't care if they're used or not. We don't have that understanding. And this is where per-class compiler avoidance comes into play. For each one of those dependencies, we have a compiler plugin in foo module that's emitting the map that says what it's actually using. And so we can have a step in the build system that checks if it's used along with the ABI jar to understand if it needs to move further down. So how does this work in practice? Well, in Java, you kind of get it for free. In Buck and in Bazel, they don't care about it as much today because it's a little more parallelizable. But in Kotlin, we built this for Buck, and we upstreamed most of this to Bazel. And so this is open sourced right now in the Bazel repo. It's used in Bazel today just for JDEPs, which is it helps identify if you have unused dependencies, but it's not using it for per-class compilation avoidance. But all the logic's there, and we're currently working with the Bazel community to build per-class compilation avoidance there. But for Buck, where it exists today, it emits another output, which is use classes, and then the build system uses that to identify if it can skip any of those targets. So here's what this does. It's a Kotlin compiler plugin. It extends the analysis handler extension and the storage component container extension, so it registers itself. And then it registers a call checker, which declares declaration checker and call checker is the 2. And then for every visit that this receives, it adds them to a map. So it has like a class path resolver. It says, hey, for these calls or these KT declaration, let's go ahead and hand these to a map. And then when it's done, when the analysis handler is completed with the event, we take that map and we convert that into the format that the build system is expecting, and then we can output that. So we talked about a bunch of things for making builds faster. Let's move into one more. I talked about how Kotlin has slower annotation processing. So to round up kind of what the state of the world looks like for annotation processing or code gen for Kotlin today, we have capt, which is slow. We have Java annotation processing, which is fast, but it doesn't support Kotlin. And we have Kotlin symbol processing, which is fast, but it's pretty early. It doesn't have wide support yet, and it requires custom integration by all of the annotation processor authors. So with capt, why is this slow? Well, if you have a module, and you're sending that to Kotlin C, then you have capt as a compiler plugin, and it runs in 3 steps. It creates stubs, it runs annotation processing, and then it does compilation. And then the output of that is both your class file and your CodeGen class file. But capt slows down builds significantly. We observed over 150%. over pure Java or Java with over pure Kotlin or Java with annotation processing. But if you remember from the mixed source set diagram, this factory typically runs all the Kotlin stuff, then the Java stuff. Maybe there's some optimizations we can pull from this, right? If we could just get rid of capt altogether and run that in Java-C, maybe there's an optimization that we could extract from this. And that's kind of what we did. So we built a custom compiler plugin for Java-C called Captish. And what this does is it uses a Java-C flag that runs annotation processing on classes directly. So we have Kotlin C that runs only on your source files. It doesn't do any code gen. It outputs a class file that retains the annotation. That's then handed to Java-C, and Java-C is told, hey, run your annotation processors both on Java-C and on class files, which is in its standard mode of operating. And then Java-C is able to output code generation that was declared in your Kotlin files. And this works. It's very simple. So Java-C can do this by default. It's a command line argument. We have a compiler plugin that simplifies this a bit more. All this does is it takes the classes that you've told it about and it adds it to the class path for code gen, for annotation processing. Of course, it has some downsides. Because you're running in a pipeline, Kotlin, then Java, you can't reference directly generated code in the Kotlin. It has no context of it yet. That was a fine trade-off for us. We're able to work around that. Most annotation processors don't have this requirement, or if they do, it's in a very minimal number of spots where you can get around it with reflection. You have to have class-retained annotations. If you source-retained annotations, they're dropped from those class files when they're produced, and so you don't have anything for Java-C to run. And you can't generate Kotlin code with your annotation processor. It's doing the compilation in Java-C, so your code gen needs to use Java Poet instead of Kotlin Poet, as an example. So we've talked about faster compilation, a bunch of these. There's some future-looking stuff that maybe would be good for another talk, our investment into KSP, what we're doing about the K2 compiler, and then we're doing some interesting graph work to try to flatten our build graph and make that a little more understandable. So let's move on into talking about IDEs and dev tools. So quick recap, we give folks, they have a standard local development setup at Uber. They get an M1 Max running Mac. They're using IntelliJ 2022. We have a custom set of IDE plugins. We're automatically setting the IDE up and the VM options. We have LDA integrated, which is our analytics pipeline. And then we're managing that with Chef, which is an IT pipe for setting and installing applications. But this is error prone. It still requires developers to set up some of their Android environment, and they can have old versions of the IDE or different things like that. Custom IntelliJ plugins, we write a lot of these. We have our pipeline for analytics. We have a lot of scaffolding related stuff like create a new module or create a new architecture component. We have explorers for our DI. We have a real-time architecture explorer, which is pretty cool. And we have a real-time UI updating tool, which we'll talk about now. So we built this thing called Quick UI, which is pretty neat because it allows us to do hot loading of XML resources directly. So what this does is when the user runs build, we check if they've only changed resources, and if they have, then we run it through a separate pipeline. And that separate pipeline just assembles those resources into a shim APK, and then we install a second APK beside the main one on the device, like Espresso does for running your tests, that just holds versions of the different resources. And then in our app, during development, we have a custom resource wrapper and a layout inflator that's able to load from a custom location. So let's give a quick demo. Let me find my mouse and here, let me. Come on. Seem to be working. Okay. It doesn't like being full screen. Sorry. You'll have to squint. So what we're doing here is we're changing an XML resource, and then we're running a command. When we run that command, we see the app doesn't restart. It just immediately swaps out that layout. So in this case, we've taken the XML resource, we changed the text of it. Now we're making a second change, we're changing the margin. We change the margin here. We run our build with quick UI, and as soon as we build that, it takes seconds and it's changed the margin. So compared to a standard build for the application, which may be 30 seconds or more, this takes a second and a half. Okay, let's move forward since we're running low on time. So I want to introduce a cool thing that we built called DevPods. So DevPods is our cloud IDE solution that's built on top of Linux servers that are really beefy, like GCP servers. We automatically provision them for our Android development and all of our other flavors. So they come fully batteries included out of the box. They have the IDE running, they have build snapshots set up, they have the IDE indices ready to go. They're automatically running it as well, and then we control things like we can automatically turn them down when they're not being used. What is really cool about these is it allows developers to have instant context switching. So you can run multiple of these at one time, and I can have one branch on one server and I'm running builds there, and one branch on another server running builds there. And I'm using the local IDE client, so I don't, my experience is the same. And my laptop isn't steaming because it's running on all of its cores trying to do a build, and I can have multiple, pieces of very different context running at the same time. What does this look like? Well, DevPod is a Docker container. It runs inside Kubernetes and GCP. It uses NVMEs, so they're very fast disks. And then we can load multiple of these onto one server and then track the usage utilization to rebalance these across different dev servers, or dev hosts if we want. And we can put these where all of our developers live. So we have major Eng hubs around the world, and we're able to set up regions with these dev servers around the world. We have standard flavors for all of them. So we have 5 monorepos. Each one of those has a standard flavor that comes fully set up. And we also allow custom workflows. Developers can add on their dot files. It's all automated. It's pretty powerful. Some really cool optimizations we built. This supports emulators and devices out of the box. So we're able to use SSH port forwarding with the ADB daemon so that we can connect an emulator to one or more DevPods at once or physical devices. Now, one really cool thing we built is called snapshots. So we boot up on a cron, a nightly DevPod. We get the IDE running, we do the full build, and then we take all of the output directories that are temporary, like the .idea folder with the IDE indices, the caches, the artifact store, and we compress all that, upload it, and then every time a developer starts up their machine or nightly, we're able to extract those archives, and we can then get them instant IDE indexing. So you might have said, well, JetBrains has shared indexes, why do we need something like this? And this is our test from the Android monorepo. If we let it fully index, we see it takes about 38 minutes for the entire monorepo. If we use the JetBrains shared plugin, it takes about 32 minutes because they still have to do a bunch of manipulation with the data. It's expecting relative paths, and it doesn't understand that everything's running on the same configuration. But because we control this configuration entirely, and every single machine is identical, we can literally just extract that snapshot and be done with it. And so this means that the IDE boot up time and the indexing time literally takes seconds. So if I don't run out of time, I'm going to give this quick demo, and then I'm going to skip the reliability section. So here's a demo of DevPods running. So we have an emulator on the left. I ran a command to start a new DevPod. So this is starting a new one called DroidCon. Now, that's going to take a few minutes to boot. So in the meantime, I set up another one. We can see from running a command that we have multiple servers running. I have a few set up for demos. I have a DroidCon New York Eats and a New York Writer. And so those were set up a few minutes before. Those are fully booted and ready to go. So I'm going to SSH into one of these, into the Eats one. And you can see I'm given some information. I'm given different URLs to connect. I can see there's a JetBrains gateway link, which is their thin client for doing server development. There's VS Code. There's a projector link. So I clicked the gateway link, and this is going to open a fully indexed, ready-to-go IDE very quickly. So this has many thousands of modules already indexed and ready to go. So this is done. That's ready to go at this point. It's fast. I can write code. I can explore the project. This is because everything was running on the server as a daemon, so I'm just connecting to this thin client. Now what's really cool is, and you can see here that it is analyzed. We get all that information. So if we go to this other machine, we switch over and we SSH into the writer one. So we have 2 dev pods that are running at once. Now, what I can do is I can open a second one, and now I have 2 full IDEs open. Both of them have full project scopes. They're both huge, huge projects. The local machine isn't suffering at all for this. See, now you can see I have the full writer project, which is a separate set of many thousands of modules that are ready to go. Now I'm going to do a quick demo of installing the application. So we have a command that forwards ADB to the dev pod. So we're going to run that in init ADB to the eats dev pod that I set up. And once I've done that, if I click back into the gateway client, you can see that the emulator is detected. If I click logcat here, I'm getting logs. This is the local emulator that's running on my machine that's connected to the dev server at this point. And so I can run an install, and that's going to take 15 seconds or so. Let's get that going. I did think about doing this as a live demo and then remembered how conference Wi-Fi was and decided to record this as a video yesterday. There we go. So you can see the quick UI. It said we didn't have any changes. It doesn't need to run. So now it's doing the full build, but there's no changes here, so it's very fast. It took 1 second, and the rest of this time it's sending it over the network. So it requires fast Wi-Fi, but that launched the Eats app right away. Okay. We're running low on time, and so you've seen most of what this can do now. I do give a quick demo of showing the writer install. So let's click on. Okay, so we're going to cut the reliability section, and I'm going to mention here that we have a set of resources. If you want to look this up later, I'll post these. This has a lot of the open source repos we talked about. It also has napt, which is an open source version of the Kotlin compiler plugin that skips annotation processing we talked about. We also have a DevPod-like product called getpod.io and coder.com if you're interested in the Cloud IDE experience. So with that, I'm done.